Can we find a continuous function, f of x, that is defined for all real numbers, and apparently its derivative is also defined for all real numbers. We ask that its derivative is always negative, and it passes through -3, -4, and 3, 4. Okay. So somebody's asking, can we find it? If we can find such a function, the correct answer would be yes, and then we'd give an example. If we can't, we'd have to show why. Why this combination of continuous, derivative has to be negative, and pass through these points, why that just can't work together. And it turns out we can't do this. We're going to have to approach this with the mean value theorem. So let's suppose, so we're going to do what's called a proof by contradiction. Suppose such a function exists. We see this function is continuous. It's continuous everywhere, but I'm going to focus on these points here. So we're going to say it's continuous on the closed interval -3, 3. Okay. It is also, it's a little more implicit in the statement, but because they say for all real x, f prime of x is less than 1, that does mean that f prime of x exists. Because you can't have undefined being less than 0 here. Okay. So f prime of x being less than is 0 here does tell me that it is differentiable at every point. Okay. Specifically, it's differentiable on this open interval. So this function here, if we had one, satisfies the mean value theorem. Okay, so what does that mean? Well, then there is some c in the open interval that we have distinguished here, so that the derivative evaluated at c is, what is it? It's fb minus fa, so 4 minus -4 over the 3 minus the -3. So that's going to be 8 over 6, 4/3. Now that seems like a nice innocent conclusion, but what do we know about the derivatives? They always have to be negative. And yet here we've shown that there is a value when plugged into the derivative that is positive. So we might say, but we know for all x, f prime of x is negative. So we see that 4/3 is f prime at c, but c is a value, so it must be negative. This is an impossible conclusion. And so the way a proof by contradiction works is you make an assumption, you suppose such a function exists, and you show that that leads to utter nonsense. Okay? If you make some assumptions, do some deductions, and you get an illogical statement, then that means one or many of your assumptions must be wrong. Okay? Or maybe just that combination of assumptions doesn't work together. Now, we only made one assumption. We suppose that such a function exists. Okay? So we were wrong in our assumption. No such function can exist. And so the answer to the question is no. You can't have a function that's continuous everywhere, always has its derivative exist and be negative, and pass through the points -3, -4, and 3, 4. We can even visualize this. Okay? If you always have a negative derivative, your function must be decreasing. But -3, -4, you can put that down here. 3, 4 would be up here. If it's continuous, you'll have to have gone up to the point. You will have to have increased at some point here. We don't know where you'll be increasing, but you have to increase. Okay? But we're assuming that the function, based on the knowledge of the derivative, must decrease. And so that just doesn't make any sense. Okay, so you can explain it that way, but it's not as precise as our proof by contradiction.